Hi guys, do you want to learn how to make a great storm effect where trees move and you have snow and dust and debris? Then you came to the right place. Guys, do you want to join a really nice server? We have tons of different channels. We have effects, modeling, loop dev, compositing. We will have resources for every type of discipline. So hop in and have fun. Okay guys, so once I open this file, we're going to have some basic stuff. For example, to start with, I created a grid, and you can see this grid is really flat, and if I take a closer look into the wireframe, you have a ton and a ton of polygons, because when I add a mountain sub, we can displace this a tiny bit. So we have a nice structure for our ground. Then what I did is to create the following in the ground mesh. Basically this is grabbing this null. I extruded volume and I created a collision source with these settings on volume. This is for our pyro solver that we're going to make in just a tiny bit. We have our SDF call and our polygons, but we do not want to have so many polygons, otherwise our simulations are going to be slow. So we're going to poly reduce this 10 times. This is way better, and let's continue to the other one. I also created some rocks that we're still not going to make. We're going to make it just in a tiny bit, but basically it's the same setting. You create some collision source, and it's up to you, but I usually leave the fill interior on, and you create these two nulls so you can reference them. And here we will see how to create custom velocity fields and how to properly visualize them. So to start with, let's create our rocks. We know we have our ground, right? So what we can do is to create a scatter node. Let's create around 1000 pieces are going to be okay, and let's scatter these rocks around with a copy to points. This copy to point is going to consist on, well, basically a cube. You will see everything is pretty much the same. So we want to randomize these values. We want to run them with a float called p-scale. This will go from 0.4 to 2 perhaps. This is nice, I guess. We need to check out the geometry. Perhaps we have too many rocks, so let's do, I don't know, 500. And this is okay. We're going to set a connectivity, or better even, we're going to do for each connected piece. We will do the following here. We are going to iterate over each piece, and we will turn them into a BDB from polygons. We're going to export this into the surface. We have this amount of polygons. Perhaps we're going to need even more. This amount of voxels, my bad. And perhaps we're going to need a little bit more. This is okay, and we can do a volume bop. And to finalize this, we can do a BDB convert. This works as follows. We're going to deform this here, and we're going to convert this back into polygons. We hop in here, and how do we try to work over the surface field? What we have to do is to export that field with a name called surface. So we can export everything we want. If we do a P and we export the surface, we should be seeing here basically nothing unless we apply a float. Once we apply a float, we can see this gets deleted. So how do we make something useful from this? Let's create a bind. No, let's create a volume sample. This volume sample is going to be plugged into the OP input 1 with the position here with the name basically called surface. So this is basically bind import, bind export, nothing more. How to create a noise? A noise with a flow noise. if we plug this in here, we are going to have an error. But if we add this with this one and we connect these two positions, we will have this, which is very cool. We can mess around with this a little bit. It's up to you guys. You can have any type of noise. This is only a basic setup, and this works flawlessly. If we do a for each at the end, we can see, if we toggle this off, that it starts to calculate here the pieces, and it will go on and on until it reaches the end of it. Now we have tons of square rocks. We can obviously change this for a circle or for a sphere, and now we will have different shapes. I prefer the spheres. See, this is way better. Okay, so now that we have this, we can make a null called out rocks, and you will see we will have this one set to SDF and to polygons. This will basically be for it to create what we need for our simulations. So remember, be organized. With A and dragging downwards, we can do this kind of alignment, which is really cool. And with Shift O, we can make a better outliner for this. So let's create a wind force, right? We need something to drag our pops and our volumes and our future trees, which is very interesting, to the side. So I know we want to have this mesh as our bounding box. So we can object mesh this guy here, and we can in fact use a bound to have the boundings, and we can do the upper bounding to 20 meters tall. This will be called out B box, just so we know this is the bounding box of what we want. We will turn this into volume called density, called bell, and this will become a vector. If we go to into the flat shaded, once we have something inside, we will start seeing a bounding box. If we turn this into a BDB from BDB convert here into a BDB, we'll see this bounding box, which is very, very cool. So remember this thing we'll plug this here, and we can see we have a velocity y, x, and z. So we got to BDB merge BDB vector from scalar here. So if we combine this, we'll only have one field, which is now a vector, and we can plug this here. This is basically a grid with a match size with these options. You can offset it wherever we want. And what this is going to do is going to create a scatter, and we're going to see how this velocity moves. We're going to grab this velocity and we will see it here. So far we got nothing to see, but if we make a velocity, a volume velocity, and we plug this in here and we add, for example, a coral noise, we will see some distortion. This is where the noise is going, and it's very, very useful. So we're going to make a swirl size of 33, which is what I want, and a constant velocity on the x-axis. Hence, it's going there. I also want to have some way of controlling this apart from here. So we're going to use our volume bob again. Let's plug this in here. And what we want to do is to basically control the velocity field. Remember to click here when you are outside. So we want to export this bind, export a velocity. If we plug in this here, we will see, if we do a 3 float vector, that it changes from 0 to everything else. So this is very cool. We know this is working, but we want to bind the same thing, which is called velocity. So this is a one-to-one, and we want to multiply this. We want to adapt this to where? If we do a rel beatbox and we plug in this one here and this one here, we'll have a bounded box going from 0 to 1 on each axis, x, z, and y. So if we plug this in here, we'll see something really strange going to the right, which is basically a gradient. But we only want to grab the y gradient, so let's vector to float this out. And let's plug this in here. Now we're going to have a 0 to 1 multiplication, and if we run parameter this out, we can do a spline, go outside, and change this as we want. See, this is very useful. And perhaps we'll also need some more subdivisions to have more detail. So we can do some things like this, which is very awesome. We can advect more or less, and well, when we don't have any velocity, we will cut the volume downwards, see? But we can obviously have a little bit of velocity at the bottom, just in case. So if we go here, we can move this around and multiplicate everything. And this will be called, with a null, our out B wind. Shift O, A downwards, and we have our velocities. So we have everything we need. We just need to make... So we have everything we need when it comes to velocities and collisions. We need to make our source for the smoke simulation, and we're going to set it here at the right of our simulation, going from right to left. So we're going to object merge this with our bounding box, and we're going to match the size with a box that is 8.5 meters on the x-axis. So if we do the following, we can have, for example, a justification on x at the minimum, and a scale to fit, not uniform, and we won't scale the x, right? So we have this as a volume or a container. You can do even less, 8 for example. This is going to be fine. This is a fast way to create a constant and procedural source. We're going to create an ISO offset. This is very interesting for density without uppercase. We're going to set 100 uniform samples, and we're going to use a volume bob again. This tutorial is full of volume bobs. So let's hop in. And basically what I want to do is a turbulent noise. The position here, we're going to just multiply our density with this turbulent noise, and we're going to promote parameter this out. We're going to have a 0.1, 0.1, and 0.1 on each axis, with a 0.5 and 0.06. So we will have these kind of shapes, which is, they are cool, they are nice. And we're going to have the original purling noise. So you would ask, why are we changing this? Well, so you might ask, why did I promote this out? And I promoted this so we can change over time our noise as shown here, right? This is going to be our source. So with a null, just so we remember, this is going to be our wind density source. But we also need some way of controlling our velocity, because we don't have any velocity here and we want an initial velocity. So let's create a volume. In this volume, we're going to have our great vector, which is called velocity or vel. Initial value is going to be 0.8, And as you can see, we don't have any width because we need to set this to non-square. It's strange, I know, but it works. And we need to volume bob these two guys together, like so. So we're going to hop in, and we are going to straight out of nowhere export this value, which is bind export our velocity. So in this case, we don't have something or a noise to output, so we're going to create this. We're going to have a constant to start with. This constant is going to be a 3 float vector, and we're going to, on the left, so 1 on x. And let's plug this in here. So we're not going to see match here unless. So we're not going to see match going on here because we already have a velocity going to that position. But we are going to multiply this by a value. And this value is going to be up to us. We're going to promote this just in case. To start with, this is going to be 1. We can expose this node and call this as mult b, mult b. Let's go outside. 1. There we go. But we want to add these two guys together, which, for example, now we're going to make a noise. Turbulent noise. There we go. On the position. And let's use our tool we have here to visualize this, guys. Remember, we have velocity, but we don't have a vector or a BDB. So let's convert BDB. Here, this will go into our BDBs and vector and merge float vector BDB vector from scalar this out. Now we're going to see something. So we want to have a 3D noise. This will be set to 0.1, 0.1, 0.1 with an amplitude of 30 and a purling noise as before. You will see this works just as the velocity from volume. We can multiply this more or less in case we want to have a bigger output velocity. And what we want to do is to only have velocity where there is smoke. Volume sample. Here we're going to do the same as before. Op input but 1. This is going to be the position, and we're going to set this to density, and we're going to multiply this vector by this scalar. So now we will only have this. This should be the second one, my bad. So now we should see, if we go here, some pockets, some holes. We can test this if it works by, for example, multiplying this by a float here, which is 0 at the moment. And the more we multiply, the more velocity we have, see? So we know by a fact that this, in fact, works just fine. So if we go here, we can, for example, change this grid for a new one and manually visualize this. So we can actually appreciate the pockets, which I'm not seeing many of them. So we can see this working if we multiply this various times. Right here, we will see these guys better if we reduce this. So these spots here are supposed to be where this is multiplying. So if we add a mult constant, we can increase this by quite a lot. For example, doing the following will increase or exaggerate these pockets. So now that we have this, whoops, I forgot to add this one here. Now that we have these pockets, we can continue and merge these two guys together. Merge this one with this one, and what we want to do is to have both of them together. This will be called out volume source. Shift O, and we are done with our source, and there we go. So now we have everything we need in for our volume sources. So let's start creating our first top network. This is going to be our smoke emitter. Let's hop in. Let's add a sparse smoke solver sparse. Let's plug this in here. Let's basically add the following object, sparse object. We plug this into the left side, and a volume source right at the sourcing. This is going to be source. So let's start by watching our simulation. So far nothing. Let's create our smoke. This enlarge fails to contain sources, and let's remove the temperature since we do not have anything. Our source volume is called bell. In fact, I know because we did it right here. See, it's called bell. We only have 1000 voxels. So if we want to have a little bit more resolution, let's add 100 here. So let's hop in. And modify this guy, because we do not want to have volume outside our container, which is the out B box right here. See, we want to have everything inside here without messing too much. So let's do a centroid. Oh my god, this was centroid from our out B box, and we will use our DX here. We will see this will output a number. Let's change to Y, and let's change to set, and we'll have these numbers moving. And we also want to have the B box, our B box of the same, of the out B box, and we will be using DX, and we'll be using the X size here. We'll copy and paste. Oh, this one, our DX size is not working. Oh, this is working. Okay, so we will copy and paste this everywhere. This is going to be the Y, and this is going to be the Z. We're copying and pasting our values as a max bounding box. So if we press play, we won't see anything because we haven't loaded the sub object out density source B box. No, we want to have our out volume source. Let's try this again with a scale of 1 or 2 perhaps. We have this volume which works just fine. We're going to use a 0.25 in this case, and we're going to input these three things, which are basically the same. I'm going to explain now. This is the ground, and we basically loaded our out ground SDF call, which is the following. Remember this one? This is this guy here, which is a collision for our volumes. It works just fine with the collision source. The same with the rocks, and the same with the rocks. We will also input our out B wind, we will use the following. This is the ground. We load this here and we click on collision. You don't need to do anything else. We do the same for the rocks. It's all the same. If we have a collision velocity, we will move this. It's not meant for this tutorial, so it won't happen anything. Just leave it as normal. So ignore these two guys. And on the wind, we are going to input our wind, out b wind, which is this one right here. And what we're going to do is to actually just have a velocity set to bell and bell here, nothing else. If we plug this into our forces, we will see that it starts colliding and it starts being a little bit more laggy because we have more resolution. But as you can see, if we visualize for example, the collision, we have our beautiful ground. Now that we have this, we can move to more distortions. For instance, right here, we can add some vortex confinement. This one will be set to 2, and disturb this one set to a block base of 1, and we will plug this in here. We will see immediately that this will start making really nice and interesting details. If we want to see this better, we can hop out of it and import our fields like so. Drag this here and set this to object and this to smoke. We'll see the smoke. We can add a light so we can see this better. This is our beautiful smoke. With a volume visualization, we will actually see our density. If you see the smoke wrong or you don't like how it looks, you can modify a couple of settings here. For example, you can go to the texture, increase this to 1024, this to full HDR, and enable the HDR rendering. You will see you will delete our fringe, so save as default. Now that we have this, we're going to BDB convert as usual, and we will set this to BDB. We'll also do a primitive properties, set this to volume BDB, and turn this on. And before that, vector from scalar, and we will merge these guys. We don't need the temperature because we don't have one. And what we can do now is to save this. I already have one node. This is the labs node. You can also have the file cache normal one. It is the same, but it has some wedge in here, which this one doesn't have. And what we did is to create this simulation. The simulation is set to here on 0.25. So we can see we have our velocity and our density. If we visualize this, it looks very nice. See? We can also do a null and export this with out wind high, and we want to have an out wind low without the need to resimulate. So we're going to do another node, which is called outwind low here. So we're going to have another node, in this case wind low. This is the copy paste, and you tell this to be wind low. Remember guys, if you want to configure this, set this to heap and cache, and the base name set to $OS. Always set to $OS, because we will have the name of the node, copy and paste here. See, this is with middle click. We'll have this frame range. Remember, try to have a pre-roll. So let's go 50 frames before, and let's start this on the frame -50. So our nodes will load from -50 also. This is what we're going to save. In this case, we don't actually need to have this one, so let's set this to 0. So we only save from 0 onwards, but we are going to simulate regardless from -50. So let's do a resample BDB and set this to use voxel size and leave the voxel size to 1. You will see this is our high resolution. This is our low resolution. We only want to keep this for our velocities and to pre-visualize. So it will end up looking exactly like that. So this is our velocity from the volume from our simulations. So let's do a Shift O and let's save this. Let's create our particles from this. So let's object merge our density source. This is our density source, and we will see we have this because we can scatter some points inside our density. Let's not relax this one, and let's add way more points. This is a lot and is pretty much what we want. We have 1 million. Let's add these two noises. The first one is going to basically modify our CD, which is a float, and we're going to remap this and play with the values. See, this is very cool. We have a really nice contrast, and the noise is a simplex with the element size set to 4, around 4, with an offset of $F divided by 2, so we can see it moving over the time. We're also going to have a terrain with these settings. Without this will look way smoother, which we don't want. We want to have a terrain, and we will have a warping, which adds a little bit of juice here. So this is very cool. The other noise is basically the same with another noise and another offset. Nothing more. It's literally the same and with a multiplication. So we have less of everything everywhere. Nothing else. This is very simple. So we're going to have a node with a rectangle. We will delete points here. So if our CD is less than our CHF, which is going to be the thresh of CD, we're going to delete our points. Remove point where here at $PT_num. I wrote it wrong. Num, there we go. So we should see something like this, 0.08. We'll only have our brightest points, and we will have our replicate node here set to quantity of 15, shape of 0.02. Otherwise we will have shapes really big, and we do not want this to be so big. And we only turn on and off this noise, and we remember, this is very important, copy our attributes. Otherwise we won't have our CD or anything we want, of course. And since this is going to be very slow, see, I'm moving the timeline, it's very, very slow. We're going to do a cache of this, so it loads very fast. These are the same settings I have in my main file, so it's going to work very good. Remember, it's the same as we did here. This is going to be called out particles source. So let's make another network, in this case a pop network, and let's hop in. So in this case, the way we actually want to load in our collisions is a little bit different. We're going to use static objects, and we're going to merge this here. It is not necessary. What I'm going to do, which is going to be actually calling or loading our proxy volumes. I usually do this because it's a nice workflow, but let's, for example, load this out round polycall, and let's also load our proxy volume, which I repeat is not necessary here, but I would like to do it regardless because these work with flips and it works very good. Even though this is not a flip simulation, it can work with a flip simulation. So round FDF call. See, we have this. And we go here and use a volume collision. So this is going to be our ground, and this one is going to be our rocks. And our rocks are going to be basically a change of name here, set to rocks. And here, set to rocks. Let's move to the first frame. We see this works perfectly. In fact, I should be using the proxy, so it's easier to calculate over these guys. I could also make a proxy of this one. In fact, I'm going to make a proxy of this one. I don't know why I didn't before. So let's go here and do the same. We barely have to think about it. We just do a note rocks polycol proxy, and we will hop in here and change this for rocks poly proxy. There we go. So we will want to load here on all points using dops, using parameter values, our out particle source. See, they are here, and if we press play, they appear and they don't do anything because we don't have any force. So let's do a gravity here. The gravity will obviously make these guys fall down and they collide with the ground. One thing I forgot is I was explaining the flips. We should use these two surfaces here in the pops. So if we press play, these one are going to fall onto the terrain, which is very cool. Okay, so now we want to add the forces. So we want to use a pop force to start with. Set to 1, set to 0.18, and nothing else. Let's see what happens. Barely anything. Barely anything. They are moving a tiny bit to the left. Okay? Tiny bit to the left. Nothing more. And we will use add back by volume, which is going to be our main source in the simulation. We're going to use our proxy volume wind low. This is going to be treated. We're not going to treat this as a volume, and we're going to set this to 2. And let's see what happens. Immediately, we are appreciating a really nice movement. It is going to take a while to load. So what we can do is to use a delete and see what happens with a delete by range set to 30 to 31. So this is going to delete the majority of the points. If we set these 2 points, we'll have 2000s. And let's see how this develops. We'll have a very interesting noise, but everything is going everywhere, and we only want to have things inside this box. So let's add a subsolver. We're going to use an object merge, and we're going to use a group. This is a really nice trick, guys. We're going to group this with the points, set to bounding by object, and with this merge, we're going to use our out B box. See, and we're going to blast everything that's outside our group, like so. So if we press play again, we will only have particles inside our beautiful box. There we go, very nice. So if we delete this, after this, we want to have a natural delete with these settings. Otherwise, we will have a ton of things. This is very useless information, at least for what I want. So I only kept these guys together, which is basically what I want. So let's do the same. Let's save this here. This is going to be my first version from the frame 0 onwards. This is the old one, and this won't collide with the rocks, so I'm going to simulate again, and we will see how this develops. So I'll be just in a bit. Okay, so we have this nonsense of points. How do we interpret this so this is, I don't know, a tiny bit better? So what we can do is to create a wrangle. And pay attention, guys, because this is going to be a tiny bit, little bit technical, but it doesn't matter. You follow along and you will be just fine. So let's create a float, which is going to be called r from radius, and it is going to be called also r from radius. We're going to copy and paste this, and we're going to set this to, oops, and we're going to set this to int max points, and this is going to be max points 2. Let's create these two guys. Oh, this is going to be a CHI, in fact. So we're going to delete this one here, discard this one, delete parameters. There we go. So now we have an integer and a radius. Why do we need this? Because there is a function called PCFind, and we will use that one. So let's do a handle. Handle is a place to store an array, for example. Handle, this is for array, and we'll use PCFind. PCFind works on this geometry. It looks for this attribute along this position with this radius and this max points. That's about it. We have our handle. Now, how do we control this? On the color, let's do an FCD. If the length of our handle, not the length, but the length, there we go, of our handle is divided by our max points, which we are going to turn then into a float, and this will give a gradient going from 0 to 1. We will see this working. So one thing I want to do is to only have our pop up here. Oh, so export the everything. Okay, so I made a mistake. We should have this before. If we simulate this again, we will have basically only what's being called our stream first input, the opposite. There we go. Imagine this doesn't exist. We should have added this before. So we have our points and we have a configuration. So if we increase this, for example, to 5 points, we will see something really cool going on. We'll see that all the points which have nearby companions or neighbors are getting turned on, are getting lightened. So we also want to multiply this by a CHF called mold, and we also want to multiply this by another thing, which is going to be our fit of our length of our b at b. Then we know that this goes from perhaps 0 to perhaps 145 or 150, and we will clamp this from 0 to 1. Let's see what happens after this one. I think I forgot to add, there we go. So now we can see basically anything because we haven't loaded this to 1. Now we see the faster ones going way brighter than the slower ones, which is very, very nice. A nice addition. We can multiply this by a factor, and what we want to do is, so we don't have over a 1, we can clamp this from 0 to 1, just in case. So we are still not seeing much, but we can, for example, do a by 3. Now we're going to see some really nice streaks of particles, and we can remove all those that are very dark. If the float of CD is less than the CHF of our deal thresh, we're going to remove 0.0 at ptnum. There we go. So let's control this as we want. We will only see what, or we will only have what we need. This is very, very interesting. And I think this can work. Okay, so we have this, we can work tiny bit on these guys. So we can have only the particles we need for our snow. And with this, we're done with our particles. Particles. There we go. Shift O, and we are ready to go with our second simulation. We are also going to have this guy, which is our tree, which I downloaded from TurboSquid for free. And I deleted these values which we don't need at all. In fact, we don't even have this to start with. But we do want to keep our name, but we don't want to keep our bar map. And we are going to convert this just in case, because you sometimes need to do that, even though this is an FBX. So what do I want to do? I want to have the branches. So let's start by splitting this. We know that if you go to our primitives, we have a name, and the name have these guys, branches and stems. So let's do at name equals anything that has branch. This is a primitive, and we will invert the selection. We're going to set the name, and I'm going to explain what this node does. So let's hop in with allow editing of content. This is a very useful node I always use. It's very, very simple. So we only have a class set to primitive and $os, in this case class. Nothing complicated about this. And we're going to set our name based on this value, which is called piece. Basically, if I change this guy to for example, branches small, we're going to have every name set to branches small. And why we added a class? Because then we add this with a string, and then by our integer to string set to our class. In this case, we have a lot of branches, so we have a lot of names. And if we want our original name, which in this case we don't really need it, we can set our name orig equals to our name. And that's about it. We have branches. If we look at them closely, set to names, we will have different colors. So we are going to do a for each connected piece, or name primitive in this case. This is going to be set to name, and we're going to do a wrangle. We're going to calculate how big these pieces are. So we're going to set the following. We're going to grab our bbox. Our bbox is our bounding box. How big is this object? And we're going to set the bbox size to this multiplication. We're going to multiply by the x, by the y, and by the z. So it's going to give out a number. This number, if we leave this cooking, is going to go into our points right here, bbox size, and we will have different values. The bigger in the scene. So why do you want to do this? Because we want to split our branches by the size. So if we make a float set to thresh and thresh, we apply. So if we add this and we copy the parameter and paste the relative, we'll have this. So if we add a bbox size is less than this guy, everything that is less than a value will go to the left. So we want the small branches. And we're going to do a pack on a single point, and this is going to be called small, and this is going to be called small branches. We'll see this on the name, and we only have one singular point representing this geometry, which is what we want for the time being. So we're going to do a null out small branches. On the other side, we're going to have the opposite, the big branches. Big branches. Out big branches. And if we split, we're going to have on this one the ellipse. And these are going to be called out ellipse. We're going to merge these guys together. Now we have 3 points representing the whole tree. But before we got to set the names of our ellipse. Otherwise, our pack is not going to function properly. There we go, like so. And this is going to be called ellipse. We always need to have this separated. In this tutorial, we're not going to use these two guys, but you can use it if you want. So let's make this larger, and we are going to have a null called out tree packed. We're going to unpack this and do a null called out tree unpacked. So this is our asset preparation. We split and we merge again because we're going to use the tree pack to scatter. Otherwise, it would take a long time to scatter. So what we're going to do is to object merge, and we're going to use the big branches. The big branches are going to be used to calculate everything that has to do with the simulation. So let's actually convert this, and let's delete a couple of attributes. We're going to delete these guys. We don't want anything that has to do with this. We can even delete the class now that we are here. The VBox2, the class. We can even delete the path. We don't need anything, literally anything. So we want to remesh this guy, and we want to do a wrangle called add a float of a height mask at, and it's going to be 0 because we only want to initiate it. We're going to scatter some points, which this is okay, and we're going to connect adjacent pieces. This is going to be set to adjacent points. This is going to be 3.8 and only 8 points. So we'll have this kind of structure, perhaps a little bit more, or even more. And I think so we can have like 2000 points being welded by perhaps 10 of these. This is fine. This is only for a proxy. We don't need to think that much about it. We're going to make a group, which is going to be called root. This is going to be set to points, and we're going to use a bounded region. As far as this goes, this is already nice, but we're going to move just a tiny bit so we can include other type of logs or trees or whatever we want to use. And we're going to use a edge transport, which is a very cool feature, which grabs from, so we can, that basically creates like a gradient from 0 to, well, everywhere. You will see what happens when we use an edge network set to group and we use our root. If we use control middle click and set to distance, we will have a gradient. This goes from 0 to 15 in this case, and we can use a wrangle to normalize this guy. So before that, we're going to promote this distance from point to detail. We're not going to delete the original, and we're going to call this on maximum to distance max. We're going to do the same with distance min, set this to minimum, and we're going to plug this in here. So what we want to do is to make a normalized ramp based on this min and max. So let's create a float norm dist set to fit of the distance by our min and max from the detail. So float min equals detail of 0 at distance min at 0, like so, and we do the same with the max, and here max. This should work with a fit set with min to max, and this is going to 0 to 1. So we can actually turn this into a density. For example, f at density. This is going to work for our wire solver. We're very close to finish this, and we're going to use the norm dist multiplied by 2. So let's go and see our distance, not but our density, and our density goes from 0 to 2 because we have this normalized multiplied by 2. We will also have our width set to our density. The width is also an attribute from a wire solver, and we will make a ramp from this. Ch ramp. This is going to be our ramp, and this is going to be the values we use in the ramp, and we can manipulate these guys together, right? So we want to invert this guy, so the base is the strongest one, or the biggest in fact, and the tips are the smallest. This will be fine. We're going to make another wrangle, which are going to be the grouping. So if the f at density is greater than hf thresh, then this is what is going to happen. I group pin equals 1, and we will also have our I pin to animation set to 1, which is basically going to pin everything together. Else, we're going to have another group called I at group branches set to 1. This is going to be our threshold set to 1.3. So if we split this guy and set to root or pin, in this case pin, we will see that we have a pin here. So if we move this guy, we will have less or more points. This floating point is in fact due to the lack of a clean here. So if we do a clean here, we will remove a floating point. So we can have this, everything that's going to be pinned set around here. The rest is going to be moving through the wind. This is only for testing. We don't need this anymore. And we're going to do another wrangle. This is if you want to use volume, for example. And we're going to use mass equals to 0, so it stays in place if we use volume. We're also going to fuse these guys together. Look at these points and prims, they change. We have less, otherwise it explodes in simulation. We'll have a name set to constraints. Now we have a name here, set to constraints, and we have our null set to out constraints. We'll object merge our tree out packed. Let's organize this a little bit more, like so. And let's merge these two guys together. And have the tree and the constraints, which they look correctly. See? Let's do a copy to points where we have a scatter set to 30. And this is the fun of packed things. We only have a couple of points, not that many, and everything is instance. So you would see we have an attribute pscale here, and we have the mesh of the ground with a small scatter, 30 points, and we have this wrangle. This wrangle contains a way of rotating our normals based on a direction. So we have a normal pointing there. We need a way to solve the rotation of this normal, and this is done with a Q rotate. So basically what we are doing is setting an ID which has nothing to do with this, and that is very important. So each tree has its own ID. When we basically distort with a point deform, we don't want all the pieces to be deforming each other. We want their name to be distorting itself. So this tree won't distort this one, and it will only distort them on its own. So we want to set this a couple of variables. The up vector being we're going to point upwards. The normal is going to be always on the z axis, because remember, if you copy to points and have an object pointing there, I don't know why, but copy to points automatically moves this guy to the set position. I don't know why it happens, but we should be setting this like that. So let's create a vector called rotation, and we're going to do the following. We're going to use a quaternion. So we're going to create a quaternion, and we're going to be using radians. So we are going to convert a number to radians, and we're going to multiply this, which is a random number from 0 to 1, by a big value. Put anything you want, just make it big. And the quaternion needs an up vector. So basically what we are saying is, okay, to which direction do I rotate? Do I rotate upwards or do I rotate there? So I want to rotate an X amount of degrees. In this case, is going to become random upwards. So this normal, we can rotate this with a Q rotate. So we're going to use this value which we created, saying rotate upwards with this normal. So this normal is going to do this. That's about it. There's nothing else we need to know or worry around. So as you can see, these guys are rotating X amount of degrees. So what we're going to do now is to blast these guys. And we're going to have our big branches, and at the middle we are also going to have our small branches, basically anything that is not selective. We have big, we have small, and we're going to also have our constraints there. So if we do the following, we can see that we have an ID, so each on their own. But we want to promote, because we're going to need to have this into primitives when we are making the deform. So we're going to promote this to primitive. All of these are going to be promoting the value like so. We're going to have a couple of nodes. This is going to be called out small branches geo. This is going to be called out big small branch is GU, and this is going to be called out constraints, but from the tree out tree constraints. These two guys are going to be merged, oops, like so, into the null called out tree. So it's a combination of both of them. So this is the full pre-setup. It was long, but we are about to finish. So let's create a DOP network. This DOP network is going to have a wire solver, a wire object, and each of these guys is going to be loading our out constraint geo, or out tree constraints. Let's go to the first frame. We have our trees, and we press play. Basically, this goes a tiny bit slow, but it works. We can try with no copy the points to start with. So this is faster. This is very fast, in fact. We're going to use a multi-solver. Why are we using a multi-solver? Because we cannot pop at vect here, pop at vect with volume. We can't. This doesn't work. It doesn't recognize it. So we need to find another way, and the way is to create the following solution. Is this plus a sub-solver. And the way this works is, okay, we have everything pinned together. If, for example, we have a gravity, we want to remain this, we want to have this not fall down as right now. This is falling down. The way we control this is by going to the wire solver, going to the wire object, going into material elasticity, and setting this to a bigger number, like for example, I don't know, 100,000, and this to 1. And in physical, we can go and set the width to 0.1. We can actually visualize this in the visualization with the width. You will see at the bottom we have this interesting shape, and the taller we go, the thinner it is. So this basically controls the whole behavior. We should just need to go here if we want to change it. So let's hop in here, set this button, and let's go inside here and move this guy as we basically want. See, we have more or less distortion or shapes going up or down. Remember, this will move this guy a little bit taller, but it doesn't matter. I like it. So if we press play, let's see what happens. So if this guy is slow, we can always go back here and reduce the amount of geometry. So let's see what happens now. Creo que lo está haciendo muy lento, boludo. So I had a mistake here when I had scale rate by, and this should have been 1 instead of 0. So if we see closely with this value, we have our functional tree moving a little bit. See, it is very nice. So how do we make an advection? Our advection should be inside our subsolver. So let's do an add tree wrangle, and we are going to do an object merge over our B1 wind low. There we go. So let's do a vector bell equals vector bell, and we're going to sample the velocity. So volume sample B, very important, 1 at bell at $p, and we're going to use B at B plus equals bell multiplied by 0.1, and this should give us the following results. So if we press play, we'll have our tree moving once the volume reaches. See, here's the wind, it moves flawlessly. Very nice. So now that we have these, we can in fact move to the opposite side, to outside, and do a switch. We're going to use object, we're going to object merge our outpick branches here and our full tree. This is going to be a proxy if you want to see the branches or you want to see the full tree. So to pre-visualize, we're going to be setting this here. We're going to blast. So we are going to unpack these so we can have our class, and we can transfer the attribute of the ID. Once we copy and paste, we will have the ID here. If we see them closely, we'll have this, and we can RBD deform pieces set like so. So if the cluster attribute is set to ID, we should see every tree moving on their own, and it looks very cool. So we got to do one more thing, which is a trial node, because this doesn't calculate as far as I know. If it does, please tell me. The velocity, we're going to set this to central difference. We're going to do two more things. First, we're going to save these tree sims. As always, set tree sims and calculate the frames you want. I'm going to calculate everything. I'm going to call this tree sim Y from YouTube. So we are going to save this into disk. So we got all our simulations here. They move correctly. And if we go to deform pieces, we have all the deformations we need. So let's do a null. And this is going to be called out trees. And Shift O, and we are done, guys. We can see everything together if we want, fast. So this is going to be the trees, like so. Oh God. And this is going to be our particles. And these are going to be our wind on high. We should do a volume visualization first, of course. So we have everything here. Very, very cool. We also want to have our rocks and our ground mesh. We have everything here. We just need to add some color. Okay, so we have this blood-like color in the particles, but everything in the scene is set up correctly. Hi guys, I hope that you enjoyed the tutorial. If you want to learn more about FX, you can join into my Discord channel down below. See ya!